Okay, we are recording. So we touched in our last class, Tuesday's class, we talked about, we introduced the idea of triple integrals. And so I think it's good to go to these illustrative pictures. There are three situations in which, well, let me just go to the illustrative pictures here. I want to, one moment, class. Let me just find it here. Yeah. So, okay. Now what you're doing is you have three integrals. The first integral is an integral that goes from the top and bottom limits are from a surface to a surface. So you see here, this solid E is bounded above by this function of x and y called u2 of x and y, and the bottom function is bounded by another function u1 of x and y. All right, and those are your limits for the first integral, surface to surface. Okay, but then if you project that solid E down into the xy plane, you get a region D. And the region D then goes the second. Well, let me just show you for this figure what the triple integral format would be. This would be the triple integral format right here. So you see dz, dy, dx. So your z limits are the surfaces. Your y limits are the top and bottom functions for that region D, which is g1 of x and g2 of x. And then d of x are limits a and b. So that's what you learned. The dy dx part is what you learned with sections 12.3 and 12.4. But you see, I want to say this the right way. Let me just put this on the whiteboard. One moment. Okay, so you have a triple integral over some solid E of some function of x, y, z, and then you have dv. dv is a unit of volume. Now, you can have dz, dy, dx. But there are other combinations as well. For instance, you could have dz, dx, dy. You could have that situation. Okay, you could have that situation. So if we go back to the book, okay, and so you see here, okay, so there now, if I guess I'll have to have a normal size. So figure 3, you see there where it's bounded above and below by two surfaces, and then you project in figure 3 the solid E down into the xy plane, and region D, you're bounded, let me see here. No, wait, hold on. Is that the right picture? See, in the textbook, it's a little easier they have it a little bit, like if you have the physical tech, yeah, this is what I want. Yeah, so let me phrase it this way. So let's say that your dv is dz, dx, dy. That's your order of integration. The z limits are your top and bottom surfaces that bound the solid. And then you project the solid down into the xy plane. Okay, and so what I'm doing here is I'm looking at this picture here, figure 4. So you project the solid E down into the xy plane, and the region D is bounded on the left and the right by functions of y. And then you have y limits. So figure 4 goes with the order of integration is dz, dx, dy. And so this would be the triple integral you would use. Now, on the other hand, if your solid were, as you see here in figure 3, solid is bounded above and below by functions of x and y, those surfaces, and then you project the solid E down into the xy plane, the region D is bounded above and below by functions of x, and then the limits go from A to B. So figure 3 would be a situation where you have dz, dy, dx, dz, dy, dx. And so in that case, this would be your triple integral. You see how this works? Okay, I'll tell you what, let's look at another situation. Let's look at another situation. And we sort of quickly went through this in the last class. Look at figure 7. Okay, don't worry about I'm not going to worry about type 2, type 3 regions. I'm just going to look at the picture. So there's a solid E, and it's bounded. Well, the solid E, the surfaces are functions of y and z. So the solid E is bounded, I guess, in front and in back by functions of y and z. And then if you project that solid E into the YZ plane, you get a region D. Okay, so in this situation, maybe I can hold on here. That would be your triple integral right above figure 7 for that region. Now, you see the dA, they've not talked about dA yet. dA could be either dy dz or dz dy, but you're integrating with respect to x first for that solid in figure 7. So the remaining two variables of integration are going to be y and z. But are you going to do dz dy or dy dz? Well, it depends on region D. It depends on that region D. Okay. Are there any questions so far? Okay, well, let's look at another scenario here. Look at figure 8. Figure 8, there's your solid E. This solid is bounded on the left and the right by surfaces, right? The surfaces are not bounding the solid above and below. The surfaces that are bounding the solid E it's a surface on the left, that's a function of x and z, and a surface on the right. That's a function of x and z. And if you project that solid E into the xz plane, that will give you your region D. So the region D is going to be either dy dx or dx dy. It depends on what region D looks like. So in that situation, this would be your triple integral. You see, you integrate with respect to y first. Okay, are there any questions on this? Who's feeling good so far? Give me a thumbs up if you're feeling reasonably reasonable about this. We're going to look at some examples. All right, Alexander, that's good. That's good. That's good, Lexi. Good, Norina. Okay. Okay. Well, so let's start off with a very simple example. Example 2 in the textbook. So here they want you to evaluate the triple integral over the solid E of z dv, where E is the solid tetrahedron bounded by those 4 planes. Now, the plane x equals 0 is the yz plane. The plane y equals 0 is the xz plane, and the plane z equals 0 is the xy plane. Okay, so you got the bottom, the back, and well, basically, the coordinate planes are bounding this solid on the sides, but then you got the plane x, y plus z equals 1. That is a skew plane. And so if you were to draw a picture here, this is a picture of this solid. So you see how the solid is bounded below by the plane z equals 0, to the left by the plane x equals 0, and in the back by the plane, no, it's bounded on the left by the plane y equals 0, and then it's bounded on the back by the plane x equals 0. And then there's that z equals 1 minus x minus y. So that's what that solid looks like. Okay, so do you think we're going to do, what would be easiest to do first? To integrate with respect to z first, or to integrate with respect to y first, or to integrate with respect to x first? Should we do dz first, or dy first, or dx first? What would be the best way to go here, or the easiest, I should say? Good, Norina. Good, Arian. dz. That's right. Because it's very clear that the surface is bounded above by the plane z equals 1 minus x minus y, and bounded below by the plane z equals 0. Okay, and I'll mention one thing here while I'm at it on this. So the region D is determined by the intersection of z, for this example 2 in section 12.7, it's determined by the intersection of z equals 1 minus x minus y and z equals 0. Okay, so the intersection let's put in z equals 0 here. So 0 will equal 1 minus x minus y. So that means that x plus y equals 1. Okay, and so, or y equals x minus 1. So if we go back to the picture, we go back to that picture they have, okay, you can see that where that plane coming down touches the plane z equals 0, it touches it along that line segment that's connected by the coordinates 1, 0, 0, and 0, 1, 0. Well, that's the line y equals 1 minus x. Okay, and so, how do you get 0, 1, 0 and 1, 0, 0? Well, if y equals 1 minus x in that xy plane, that line segment's going to start at 0, 1. And it will go to the x-axis. It'll touch that at 1, 0. And then, of course, the z coordinates are 0. Okay. And then, of course, the top plane, z equals 1 minus x minus y, when x and y are 0, z equals 1. So you get 0, 0, 1 for the top vertex. So now we're ready to, and then, of course, figure 6 shows the region D. If you project that solid E down into the xy plane, you get the region D. And the region D, you could either do dy dx or dx dy, but they're choosing to do dy. Okay, dy first. So let me see here. Now hold on. Yeah, here is the integration work. Let me see. Maybe I can have it. Take a look at the integration work. So obviously they've left out some steps, right? They've showed some steps, but look at the limits. Let's first of all focus on the limits. So the z limits are from 0 to 1 minus x minus y. Okay, in this example 2. Are we good with that? Are we good with that? Z limits are the bottom surface is the plane z equals 0. The top surface is the plane z equals 1 minus x minus y. Okay, now that you know that, you go to the region D. The region D here, the top function is y equals 1 minus x. The bottom function is y equals 0. So that's why then your limits, the y limits go from y equals 0 to y equals 1 minus x. And then finally the x limits have to go from 0 to 1. So you're good at doing double integrals. A triple integral is just an extra integral to do. And let me just see here. They work it out and they get an answer of 1 over 24. So this is the kind of work you're going to be doing with sections 12.7 and 12.8, these triple integrals. And the homework's going to take time, which is why I'm giving you a little more time for the 12.7. You just have to do it, right? You have to do it. It's part of the course. And actually, in graduate school, I did integrals like more than that, like order statistics. You can have 6, 7, 8 integrals, but I know I've done problems with at least 4 integrals. But I don't want to scare you, so we won't worry about that right now. Okay, so let me just see here. Let's go to problem here. Now, this problem, I'm not actually asking you to copy this problem down because it's in your textbook. So in your ebook, can you go and locate exercise 33? Okay, so I'd like everybody to, in WebAssign, to access their ebook and find exercise 33. It has this exact same picture. This is exercise 33 from section 12.7. And then we'll talk a little bit about it. Okay, give me a thumbs up if you have your ebook open to this problem, exercise 33. Good, Christopher. Good. Everybody should have it open to that. So when you look at this integral here, okay, the order in which they're doing that is dz, dy, dx. So for dz, if you look at the picture here, dz means go from bottom surface to top surface. Okay. So if I were to go from, and let me just see here, this might be, if I were to go from bottom surface to top surface, that would be dz. So what is the bottom surface? What is the bottom surface? Bottom surface is z equals 0. And then the dz goes to the top surface, which is z equals 1 minus xy. See that? Are there any questions so far? Please ask if you have a question. All right. Well, now let's look at these y limits. One moment. I am, hold on here. I'm looking for something. One moment. All right. So Now we have to get the y limits. Now we have to get the y limits, right? So what we do is we take, I want to say this the right way. Yeah. We take this surface here and project it down into the XY plane. Okay, we project that surface down into the XY plane. Now, what would that look like? What would that look like? Well, let me show you. Because, see, for dy, no, don't do that, please. For dy and dx, we need a region D, just like you learned in section 12.3 and 12.4. You know, we need a region D. So the region D okay, is going to, hold on, let me just do one more thing here. Try to get this up a little bit. Yeah. Okay. Do you see that this is your region D? One moment. Okay, thank you. All right, so here's one. There's region D. And so the bottom function here is y equals square root of x, right? That's this function. I mean, we're doing dy next, right? We're doing dy next. So dy is going to go from this, try to draw it best I can here, class. Dy is going to go this is your dy, right? Come on, get out of there. This is your dy. And the bottom function is y equals square root of 1x. And the top function is y equals 1. So this is how you're getting these limits for y. And then the x limits go from 0 to 1. See how this works? Are there any questions? So like in the projection, this point here would be like this point, right? And this point here would be this point. and this point here would be this point. How many find that helpful? Is that helpful to kind of help you see the projection? Okay, Noreena's liking that. All right, that's the line y equals 1 there. Good. So now in this problem, what they want you to do is they want you to rewrite this equivalent iterated integral in 5 other orders. So you notice they're just giving you a function f here. They're not wanting you to evaluate this, but they're saying there are 5 other orders of integration. 5 other orders. Well, let's see. We have dz, dy, dx. What's the next order we could do? dz, dy, dx is one order. We could also do dz blank blank. Right. Good, Norina. dz, dx, dy. Okay, that's fine. And then, well, we could do dy, dz, dx, right? Or dy, dx, dz. Okay. I mean, all right, so how many orders do we have here? I mean, this one here, the first one they gave us, right? Dz, dy, dx. And then we have, they say there are 5 other orders. So here's the second order, dz, dx, dy. Third order is dy, dz, dx. Fourth order is dy, dx, dz. 2 left. What's left? Okay, Lexi says dx, dy, dz. All right. And dx, dz, dy. That's absolutely right. So dx, dy, dz, and dx, dz, dy. So we have to find the other orders. We have to find these 5 other orders. So I would like to give you a little time to see if you can get these 5 other orders. Okay, that's what I'd like you to do. All right, so take a few moments. Well, it's your first time doing it. See if you can get. All right, go ahead and begin working on trying to get the triple integrals for these other 5 orders. Obviously, you got to figure out the limits. Okay, so I want to give you a little time to work on that, and then I'm going to show you the solution. Okay, but let's see what you can come up with. Let's see what you can come up with. The dz, dy, dx should be easy, right? All right, so take a little time here to work on that. And I'll be back in a few minutes. Okay, so let's come back here. All right. So let's say that we wanted to do, let's say that we wanted to do, let's say we wanted to do dx, dy, dz. Okay, let's focus on that. So in other words, triple integral of f of x, y, z, and we want dx, well, I can't believe I can't fit that. Let's try it again. I'm not going to be sloppy. Let's try it again. I really kind of, I have to do this where the picture is, you know. Okay, we want to do dx, dy, dz. Okay. So, all right, all right. So in this case, you know, we look in the direction of the x-axis, and we notice, hey, the solid is bounded in front by that surface, okay, and that surface is y equals root x, and then it's bounded in the back by this surface, right? So first of all, for the first integral, I need a surface for the limit on the bottom. That would be the front surface. And I also need a surface for the limit on the top. I'm sorry, I made a mistake here. The surface on the bottom would be the back surface. The surface on the top would be the front surface. So the front surface, let's do that one first. The front surface is y equals root x. Okay, y equals root x. Am I going to put, can I put square root of x here for the front surface? You know, I'm talking now about my x limits. That's right, Norina, you cannot, because for the, right, that's right. I need to put x equals y squared. If y equals root x equals y squared. And that's what I'm going to put for the front surface. Okay, x equals y squared. Hold on, I want to make it nice and neat. We're going to do it right here. Okay. Now we have to deal with the surface on the back. And, you know, so the front surface, again, was x equals y squared. So I'm sorry, yeah. So the starting surface, or the surface in the back, is going to also has to be x equals something. X equals something. Well, so what would that be? Well, let's think about it. What is in the back here? What is in the back here? This surface in the back. This surface in the back is just the plane in the back, right? What coordinate plane is that? Is the plane in the back the XY plane, the YZ plane, or the XZ plane? The plane in the back is the so what I'm saying, it's the YZ plane. That's right. Thank you, Norita. So again, the way I can picture this is I want to just do it. If we think about going from back surface to the front surface, and I might have to do this in green. Back surface to the front surface. Then what we have is, I mean, that's dx, right? We're going from the surface on the back to the surface in the front along the x-axis. So, yeah. Okay, now, what are we going to do? We're going to take this solid E and we're going to project it into what plane? The solid E, we got to determine our region D, right? We have to determine our region D. So the region D we have to take our solid and project it onto a plane. But what plane would we project it on? Help me out. What plane would we, man, this didn't work. Hold on. We're going to get it. Have to use the whiteout. So think about projecting this here onto a plane. What plane would you project it onto? If you push the solid into a plane with respect to like the x-axis, what plane are you projecting the solid into? Well, what variables are not being used yet? That's right, Alexandra, the YZ. So you see, here's Y, here's Z. And if you project that, okay, onto the YZ plane, what determines the boundary is this line segment back here, right? So this is going to be your boundary. Right here. And you have y equals 1 minus x. But hold on. That's not y equals 1 minus x. Not at all, because we're in the YZ plane. No. This would be z equals 1 minus y. Hold on, I just got to erase a little better. I know what I'm going to do. Let me get that 5. Watch this. You're going to get a super eraser here. How about that, huh? How about that? I think I know how to use this a little better now. Okay. So this is z. This is z. Not 1 point, please. Don't give me that. Having a lot of trouble with this today. It's not easy to select the fonts with the stylus. It keeps wanting to change. With the mouse, I have better control. Okay, so here is z equals 1 minus y. Okay, and here is, well, hold on. Wait. We're doing dy dz. We're doing dy dz. So I don't want to have a function on the top and a function on the bottom. I want to have a function on the left and a function on the right. So let's rewrite this a little bit. What I'm trying to say is that, yes, z is 1 minus y, but then y equals 1 minus z. Okay, and then here you have y equals 0. And so, you know, here's the that's fine. Here's the dx. Now wait a minute. Yeah, that's right. That's right. The dy. The dy. You have to forgive me. I just want everything to be super clear. And okay, so y equals 0 to 1 minus c are the next two limits. And then the last two limits are from 0 to 1. You see how that works? See how that works, class? Are there any questions? Okay, so we have done, what have we done? We've done dx, dy, dz, and we have, of course, given dz, dy, dx, and dx, dy, dz. Let's get the other four orders. So, okay. So we did, hold on. What did I just do here? I did dx, dy, dz. Yeah. So yeah, this is the one I just did. This one here. But see, once you get one, it's easy to get the other. So it's a little quiet. I want to make sure you're understanding. I mean, who is, these are region Ds that I'm drawing here, region Ds. Please let me know if you have any questions. I'm giving you a moment to copy before I move to the other two pages. Okay. Here are the triple integrals for dz. Well, of course, dz, dy, dx, they gave you that. But then here's dz, dx, dy. So you see dx, dy, based on, if you're doing dx, I mean, think of it like this. Think of sections 12.3, 12.3. If you had dx, dy, and that's your dA, you'd be then going from a function on the left to a function on the right. Right? And so this is what you would get. I mean, I'm trying to show you the basics, but of course, there's naturally, work on your part, right? Practice. Okay, Simon, that's good. Simon says he's sort of getting how the bounds come about. I mean, finding the bounds is probably, for students, how many notice these problems? It's not, I mean, how many are finding it's getting the right limits? That's sometimes the challenge, as opposed to maybe the integration. How many are finding it's finding the right limits? Yeah, Simon says yes to that. Norina agrees. And so this is a good exercise. Christopher agrees. This is a good exercise on showing you how to find limits. We're not going to go beyond triple integrals in this class. Now the last one, all right, Aura likes that. The last one is dy dz dx. And I will just let you, so if you take the figure, okay, if we do dy dz dx, maybe I can go back to the figure here and erase this part here. If you do dy first, then what you're doing is you got a surface on the right and another surface on the left. Because dy would go this way. Try to get this. Hold on. Yeah, this is dy. Surface on the left to a surface on the right along the y-axis. The surface on the left is y equals root x. So, you know, for your triple integral, here, da 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 da, you know, there's your function, and you got dy, and then, you know, you got then the other two limits. Surface on the left is root x. The surface on the right is z equals 1 minus y, but that can be written as, hold on, that can be written as y equals 1 minus z. See? Again, think of it like this. Y equals root x, y equals 1 minus c. Those are your I want to make sure I'm very clear here. Those are your left and right surfaces. And then, well, you come up with the other four limits, right? You come up with the other four. By taking the solid and projecting it into the XC plane. And so when you do that, these would be your, you know, the projection would look like this picture here. And if you're doing, and into the XC plane, and if you're doing dx dz, then, you know, you're going from this, you know, there's dx, going from a function on the left to a function on the right. And if you're doing dz, you're going from a function on the bottom to a function This is dz. To a function, you're going from a function on the bottom to a function on the top. Just trying to make sure everything's clear. Yes, question? All right, so this is a nice example that teaches you how to work with limits. It's a good example. And I want to do one more thing before we go on break. I want to do another something else here with you. Well, we have to get into some applications of triple integrals. Applications. So you have used double integrals to find volumes. Okay, you have used double integrals. So far here, I'll go to the whiteboard. So for the volume between a surface given by a function of x and y and the xy plane, the volume was a double integral, right? A double integral over some region D of f of xy. And let me just see here. I want to be careful how I phrase this. Let's see if I can, yeah, dA. But we recognize too that the function of xy can be written as f of xy minus 0. So what you have here is z is this function of x and y, and then 0 is like z equals 0. So really, when you learn about the volume, how to find the volume, when the integral is written as when the volume is written as a double integral, it's understood to be the volume between the surface and the xy plane. But you can write the function of xy as the difference of these two functions. This is the top surface, the function of x and y, and then z equals 0 is the bottom surface. Okay, top surface, bottom surface. But with triple integrals, okay, you could find the volume this way. See? So what's the antiderivative? What's the antiderivative? In other words, if I iterate this part here, what's the antiderivative of 1 when you're integrating with respect to z? What's the antiderivative of 1? Z, that's right, Narina. So if you end up with, you get a z here, and then you put in the function of x and the 0, you're gonna wind up with this. You're gonna wind up with this. So essentially, a triple integral can be used also to find the volume between a surface function and the xy plane. Okay? Because, you know, then here's the region D. I mean, it's fine. But also what's nice about triple integrals is you can be more general. Because remember, triple integral, I mean, in this example, we have a surface on top, which is the function, and then the surface below is the plane z equals 0, which is the xy plane. But we could have a different function, a different surface below. So we can be very general in terms of our volumes with the triple integral. It gives us some flexibility. Let me just get down here. I mean, if we wanted to find the volume of a solid, this would be how you do it. And it could be any solid. So again, the triple integral basically collapses into a double integral when you which we have been using to find volume between a surface and the xy plane. But if you had if the bottom surface were not the xy plane, you couldn't use a double integral to do that unless you use symmetry or something like that, right? So triple integral is great. And you see what they do here? You see how they sort of justify that? Let me highlight that. See that? Let me just do one thing. One moment, that's. Yeah. So now, like they comment here, maybe I won't use blue. Blue isn't so good. I'll use yellow. So we know this represents the volume that lies between two surfaces. So it's really quite fascinating what you can do with triple integrals. Now, what we're going to learn next, we're going to take a little break here, uh, and what we're going to learn next is the concept of center of mass, for a solid of variable density. Okay, this is where, so you learned in section 12.5 about the finding the center of mass or the centroid for a lamina of variable density. Now we're going to do it for a solid of variable density. Are there any questions before I stop the recording? All right, hang on a minute. Let me. Who's feeling good so far? Put it this way, how many find this interesting? Okay, Yeva finds it and Alexander finds it interesting. Good, good, good. This is really cool stuff. We're getting into, I don't know, Nora does. I don't know if you've ever seen the movie A Beautiful Mind about Robert Nash, the Nobel Prize winning mathematician. I think it was economics, his applications that he did. But at any rate, you know, if you look at some of the things he does, we're going to be getting into really cool stuff. So, all right, is section 12.7 the assignment that's due a Sunday? Is it showing in WebAssign? If you refresh your screen, it should be showing. Great. All right. I'm going to go ahead and stop the recording. Excellent. And very good.